Welcome to Texas State University's Chemistry 2330 Introduction to Organic Chemistry. I am your guide, Dr. David Irvin. We will finish out Chapter 3, Part 4, alkanes and cycloalkanes. Okay, so one thing we're going to look at now is the SIS Trans Isomerization available to us in cyclohexanes. Okay, SIS Trans isomers have the same molecular formula, however, they have a different connectivity of atoms. And that means there's a different arrangement of atoms in space, and that cannot be converted or rotated because of the sigma bonds, because we're stuck in that ring system, so we can't do a free rotation. Okay, so when we talk about the cis trans isomerization, let's start with something small like cyclopentane ring. Okay, so in the cyclopentane ring, we want to look for, if they were all hydrogens, we would not have any cis trans isomerization because we don't have the two different groups bonded to it to give us that isomerization. If we only have one group bonded to it, then we could just flip the material over, flip the ring over back and forth, and that would give us the same. Only once we have those two substituents or more do we get this isomerization available to us. So in the case of the first molecule here, we have what we call the cis configuration. And because this ring is locked in this position here, that means there's a top and a bottom. Okay. So if both of the substituents are on the same side of the ring, we call that cis for same side of ring. Okay. In the case of having the two substituents on opposite sides of the ring, that would give us what we call trans configuration. Okay, so if we were to look at that a different way, so if we're looking along the ring in this system here, where this is our ring right here, notice both of these methyl groups are down, pointing down in the substituent. Now we could take that same thing and flip it over, and it would look something like the structure here, okay? But because we cannot flip that ring around or free rotate that ring, those methyl groups are gonna stay on that same side all the time. Therefore, we have to denote them as the cis configuration because they are different than the trans configuration. They have different properties and they have different structure, okay? Again, if we look at this substituent here, again, this is our ring that we have here. We have one substituent up and one substituent down. That's our trans configuration. Okay. Another way to draw that is to use this type of structure right here. This is where we draw the ring as just the skeletal form, where we have each line indicates a bond between carbons, and the little angles are where carbons are. And then by showing them with this dashed wedge on here, it's showing that both of those groups are going down into the paper, and they're going in the same direction. So by having this skeletal form right here with this dashed line, tells us they're both going in the same direction, which is telling us we have the cis configuration on it. We can do that same skeletal formation where we have our ring here, but if we have one is dashed, that means it's going down. If we have a solid wedge coming up, that indicates it's coming up at us from the paper, and so that means they're on opposite sides of that ring, giving us the trans configuration. So instead of having to draw out our system like this, where we have to draw the perspective of where the hydrogens are and where the methyl groups are, we can draw it with the perspective of using these wedge systems and the flat ring. So again, having the skeletal ring drawn in here, and then dashed wedges means it goes into the plane, and a solid wedge means it comes out of the plane. So in this case, we could have them both solid wedges or both dashed wedges, and it would be the cis configuration. If one is solid and one is dashed, then we have the trans configuration, okay? So let's take a different perspective and look at it for the cyclohexane now, okay? In the case of the cyclohexane, we again look at from the perspective point of view here. If we draw the ring out right here and we have one of them above the ring and one of them below the ring, that would give us the trans configuration. Note that this is on the 1 and the 4 position. They don't have to be that far apart. They can be on the 1-2 position as well. Trans just says the substituents are on opposite sides of the ring. And so if we were to draw the flat perspective here, we would have a dashed wedge to indicate it was below the plane and a solid wedge indicating it's above the plane. Okay, so let's look at that other isomer, the cis isomer here. If we looked at it from the edge right here, we would see that the 2 methyl groups are on the same side of the flat ring. And again, we would indicate that by having the same type of wedges, either both the dashed wedges, or they could even be both solid wedges if you flipped it over. It's just all about perspective. The point is, when you have 2 different wedge types on a ring like this, you have the trans configuration. And when you have the same wedge types on the skeletal configuration, you have the cis configuration. Okay, so what if we represented this as the chair versus boat configuration? Okay, so now we have to think about where our substituent is, and are they both on the same side of the ring, and what would be the most stable configuration? So let's start with the trans dimethyl right here, and it's the 1,4, so they're opposite each other. And in this configuration, both of the methyl groups are in that axial position. Okay, now because there's a hydrogen here and a hydrogen here also in that axial position, these hydrogens are closer to this methyl group than if we had them in the other form. Okay, so if we were to flip this chair configuration into this chair configuration, we would now have the methyl groups in the equatorial. Both methyl groups would be in the equatorial here. And so the hydrogens that are also in the equatorial positions are now further away from this methyl group than the hydrogens were in this axial position, making this the more stable configuration. Notice, if we had these methyl groups in a different location on the ring, we would have to reevaluate. You want as the largest, bulkiest group in the most equatorial position possible. In this particular configuration, both of those methyl groups are in that equatorial, meaning that this, where both of the methyl groups are in the equatorial position, is the most stable configuration. Okay, so what if we had the cis configuration in that 1,4? Okay, no matter how much we flipped back and forth between the 2 chair conformations, whenever we have this cis 1,4 dimethyl configuration, we're always going to have 1 methyl in the equatorial position and 1 methyl in the axial position, which means that even flipping them back and forth, they're basically equivalently the same amount of energy here. So in the trans 1,4 dimethyl cyclohexane, we have a more stable conformation. In the cis 1,4 dimethyl cyclohexane, we have the same stability in both configurations. So we're going to see, this is why we like to use cyclohexanes to help us look at some of the stability issues we have and whether or not we have, because they can't just freely rotate. We can flip back and forth between 2 configurations to look at stability. Okay. All right. So our last thing here is we want to draw this in a chair conformation with 3 methyl groups. Okay, so let's figure out how to translate this into our system here. So I'm going to use this. We want to do a chair conformation, and we have 1, 2, 3 substituents, and they're all on the same side. So the first thing we're going to do is we're going to draw a chair conformation. Okay, and then since they're all on the same side, I'm going to draw them. One is methyl group is going to be in this direction because the hydrogen is going to be down. 1 methyl group is going to be in this direction. I'm just going to start with making sure I have them in the right place because that hydrogen was down. And this methyl group is going to be in this configuration because this hydrogen was down. Okay, so all I've done is translated this into a chair configuration, making sure the methyl groups are all on the exact same side of the ring. They are all still on the top side of the ring. Okay, so In this configuration, we have 2 methyl groups in axial positions and 1 methyl group in an equatorial position. I wonder if we can flip it to the other configuration and get 2 methyl groups in the equatorial positions and only 1 methyl group in there. So what we're going to do is we're going to take this thing and we're going to put this side down and this side up to get to the other configuration here. So when we do that, we'll end up with a configuration that looks like this, because that side went up and that side went down. And so in this case, this methyl group is going to come up to our axial position right here. This methyl group is now out here at it was in the axial position. So now that it's flipped to the equatorial position. And this one was in the axial position. And so it is now still on the same side with the hydrogen, but that turns it into an equatorial position, and that hydrogen is now moved down to the axial position. So in this configuration, we have 2 methyl groups in the equatorial position. In this one, we have 2 methyl groups in the axial position. Okay, so just by translating from the flat to the chair, the chair configuration, and being able to flip it back and forth, we can see that this one is going to be more stable because we have 2 groups in the equatorial and we only have 1 group in the axial. So that'll give us, we're going to do a bunch of these in our activity on Thursdays afternoon as well.